Okay, everybody, so we're gonna get started. Okay, so we're gonna go over the challenge review problems from Wednesday, October 14th, right? So these are the ones earlier tonight that I already gave you guys. We're just going to review it because you won't have another opportunity. There's no session before your exam, which is long answer two, chapters 3 and 4. And so here we have 9 problems that I think represent some of the bigger topics they could ask about. Okay, so number 1 is a classic, not really a classic, but it's an isotope question. If you want a more classic one, they have been in previous challenge problems. I can't remember the session, but ones that I've given you guys previously are a little bit more straightforward and a little bit more like what you'd see on the exam. This one is definitely much tougher than you would see on the exam, but like I like to explain to those that come to my sessions, I don't like to give you the same exact question every single time because that's not really challenging your knowledge. When they throw you a curveball on the exam, you might have a harder time adapting to that curveball if you just get the same question over and over. That being said, some types of questions, for example, a combustion reaction, is pretty much always going to be laid out in the same exact way, but ones that I can vary, I do try to vary. Okay, so you're told that cobalt has a mass of a little bit under 59 AMU, right? So it's 58.9 AMU. It has 3 isotopes, and you're given the mass of all of them. Now, you're told that the abundance of cobalt-59 was found to have an abundance, right, that is a 45% increase when compared to the abundance of cobalt-57. And then they just say, what is the percent abundance of each isotope? Okay, so this 45% increase is definitely something that we don't typically see in isotope questions. Okay, and so we're not given the percent abundance of any of these isotopes. Okay, and I had to give you the 45% increase because if not, you would have had 3 variables that weren't related to each other, and that's much too complex. Okay, but something we have seen before is when we're not given percent abundances, right, we can assign X and Y percent, right? So I'm going to label cobalt-57 as X percent, right? I don't know what X is, but I can solve for it. Now, if the abundance of cobalt-59 is a 45% increase compared to the abundance of cobalt-57, we can label it as 1.45x, right? The 1.45 is saying a 45% increase, okay? So 1.45x, and then we're going to label the percent abundance of cobalt-61 as Y percent. Now, we're told that these are the only 3 isotopes, and so when we add up their percent abundances, they have to add up to 100%. Okay, now just realize that in kind of decimal form, 100% really just means 1. Okay, and so when we add these all up, we'd find that X plus 1.5x plus Y equals 100%, or in terms of kind of decimal form, just 1. Okay, and we're going to use a substitution reaction here, right? We're going to say Y is equal to 1 minus 2.45x. Okay, and I'm going to plug this into my average atomic mass equation, because if I put it all in terms of X, I can eventually just algebraically solve for the value of X. Okay, so my average atomic mass of cobalt overall is 58.933. This is equal to my mass of cobalt-57 times my percent abundance of cobalt-57, which is X. Now to this we add my mass of cobalt-59 multiplied by its abundance. Remember, its percent abundance is 1.45 times X, which is basically just the 45% increase relative to cobalt-57. And to this, again, we add our third isotope, cobalt-61's mass, multiplied by its percent abundance. So its percent abundance would have been 1, but we're going to put in this substitution equation so that we only have one variable, X, in this entire equation. Okay, and so what I do here is I just start multiplying out right? So 59.222 times 1.45x comes out to 85.872x. And remember to multiply the 61.51. So times 1, but then you also have to multiply it by negative 2.5x, basically, right? So remember to distribute this 61.5. When you eventually solve for x, right, you isolate x and you solve, you find that x is 0.334, okay, which in terms of a percent is a percent abundance of 33.4%. And again, remember up above, we labeled x as the abundance of cobalt-57, okay? So for what is the percent abundance of cobalt-57, your answer should be 33.4%. Okay, now cobalt-59's percent abundance was equal to 1.45 times x. Now that we've solved for what x is, right, we can sub it in. And so 1.45 times 0.334, that gives us a value of, when we turn it to a percentage, 48.4%, which would represent our abundance of cobalt-59. Okay, lastly, we just have a single isotope left. And again, remember that all of the percent abundances of our isotopes have to add up to 100%. Okay, so 100%, which is again the total of all of the abundances of our isotopes, minus the abundance of cobalt-59 plus the abundance of cobalt-57 equals, this would just be our remaining percent abundance of cobalt-61. Okay? So again, a little bit harder than you'd probably see on an exam, but it's really just algebraically harder. The general concept of that substitution is definitely something you can see. Okay, number 2 is your very classic, just so classic, limiting reactant problem. So A, what is your limiting reactant? B, how much carbon dioxide can you form? C, how much excess reactant do you have of each reactant? And D is basically a percent yield. Okay. And I actually meant to give you an unbalanced equation here. So that was not supposed to have coefficients because it was supposed to test your balancing skills. And so I apologize for leaving those coefficients there, but a lot of people ask me, how do you balance problems? And there's no set steps, which I think kind of irks a lot of students. And so here I try to emphasize kind of my mindset while balancing this equation, okay? So I would start with one of the more complicated molecules, which I would say is this first reactant, right? CH2O3, right? And I kind of underline carbon, and there's a lot of oxygen throughout this entire equation. So I'm going to focus first on carbon and hydrogen. So there's one carbon here, right? I'm just going to assume that there's one of this molecule. If there's one carbon here, that means I want to have one carbon as CO2, right? So I'd kind of think, okay, this coefficient in front of CO2 should be 1. When I look at hydrogen, we have 2 hydrogens in that molecule. And when we look at HNO3, right, we only have 1 hydrogen. So that kind of tells me that let's put a 2 in front of HNO3, because now at this point, I would have balanced carbon and balanced hydrogen. Okay? But now that I've put a 2 in front of HNO3, I notice that I now have 2 nitrogens. So I'm going to kind of focus my attention on nitrogen now. So 2 nitrogens, I come over to diatomic nitrogen on the reactant side, and that already has 2 because it's diatomic. So that kind of coefficient should be 1, okay? And so up to this point, my nitrogen, carbon, and hydrogens are all balanced. And so my last step is to balance my oxygens. And so I notice on the product side, I have 2 oxygens from CO2 and 6 from HNO3, because I have 2 of those, for a total of 8 oxygens on this side. Okay, now in my CH2O3 compound, I have 3 oxygens, right? Okay, so that means I still need 5 more on my reactant side. And so when I'm looking at diatomic oxygen, if I had a coefficient of 2.5, right, that would allow me to have balanced oxygen, which again was the last element we had to balance. Okay, so when we kind of look at this rough balancing, it should have been a coefficient of 1, 1, 2.5, 2, and 1. But you can't have decimals in a balanced chemical equation, which kind of tells me I'm going to balance this, multiply this entire equation by 2, which is how I got 2, 2, 5, 4, and 2. Okay. Now the next getting to the question that was just balancing is, what's your limiting reactant? Okay, so whenever you're given starting amounts of multiple reactants, it's going to be a limiting reactant problem. And basically one of them is just going to prevent you from making more product. Okay, and so if we have 50 grams of this CHO compound, right, I'm going to convert it to moles of that compound and use my balanced chemical equation to convert from moles of my reactant to moles of CO2. Now I'm converting to moles and then grams of CO2 because question or part B eventually asks about that. Okay, so 1 mole of CO2 is 44 grams or so, and I find that based on this CH2O3 compound, I should be able to make 35.5 grams of carbon dioxide. Now do the same exact process for nitrogen and oxygen, right? So 15 grams of nitrogen, 1 mole of diatomic nitrogen weighs a little bit over 28 grams, right? Based on my balanced chemical equation, it takes 2 moles of nitrogen to make 2 moles of CO2, and that, when we convert it to grams, is 23.6 grams of CO2 that we could form based on our nitrogen. Lastly, we look at oxygen, so 70 grams of oxygen, 1 mole of diatomic oxygen is 32 grams. Based on our balanced chemical equation, it would take 5 moles of oxygen to produce 2 moles of CO2. And again, then we just use the molar mass of CO2 to convert to grams. And we find that based on oxygen alone, we should be able to make 38.5 grams of CO2. Okay? And so to find what your limiting reactant is, it's just the reactant that allows you to make the least amount of product, right? So the least amount of product is 23.6 grams, and that is synthesized, right here, 23.6 grams. That is associated with nitrogen. So your limiting reactant is nitrogen, and how much can you actually form? It's only that 23.6 grams of CO2, because after that, you have no more nitrogen to undergo this reaction. Okay. Okay. Now part C says, how much excess reactant of each reactant do you have? And so the easiest one I'm going to start with, your limiting reactant, in this case nitrogen, should always have 0 grams remaining, right? It's your limiting reactant. You used all of it to make product. Okay, so your limiting reactant, if they ever ask you how much excess you have of that, it should be 0 because you should have used it all up. Okay, now to solve for excess of your other reactants, you kind of work backwards, right? So we're going to start with how much product we could form, so 23.6 grams of CO2, and we're going to work forward to our reactants, right? So we're going to convert grams of CO2 to moles of CO2, right? That's what we do right here. Then we convert from moles of CO2 to moles of CH2O3, and then we convert to grams of that compound. And it's very important to note this dimensional analysis gives you how much reactant you used to make that amount of product. Okay, so this dimensional analysis is telling you that you used 33.3 grams of CH2O3, okay, in this reaction. And so your excess of that would be how much you started with, 50 grams, subtracting how much you used, okay, 33.3, which is 16.7 grams of excess, sorry. Sorry about that, just give me 1 second. Okay, and so we do the same exact process for our other reactant, oxygen, right? So we start with how much we were able to make, 23.6 grams of CO2, right? And we convert to moles of CO2. Then we use our balanced equation to find how many moles of oxygen that's equivalent to, and then convert to grams. And this gives us that we use 42.9 grams of oxygen, okay? And so again, to find how much excess we have, we do how much we started with, and we subtract how much we used to find that we would have had 27.1 grams of excess oxygen. Okay, Now getting into part D. Sorry, I was just afraid the recording was gonna grab my roommates talking very loudly. So in part D, they told us that we actually collected 12.8 grams. Okay, so actually collected infers experimental yield, right? Well, through dimensional analysis, we solve for theoretical yield, how much we should get. But again, in the actual experiment, that might not be perfect, okay? And so the experimental yield, which was given in the question, was 12.8 grams we collected. We found through dimensional analysis based on our nitrogen that we should have produced 23.6 grams. And so our percent yield, we just multiplied by 100 to turn it from a decimal to a percentage, should have been about 54%. Okay, number 3. So this is an identity question, but it kind of incorporates precipitation, right? So we have about 20 grams of some unknown compound with metal X, right? And the anion portion, which means phosphate, right? Phosphate is the anion in that compound, goes on to form a precipitate when it reacts with calcium fluoride. Now, precipitates are formed from a cation and anion, which means if phosphate, the anion portion, is reacting with the calcium fluoride, the portion it's actually going to react with is the calcium, right? Anion with the cation of calcium, okay? And it says that it makes a precipitate and they react completely. That's just to kind of tell you that there should be no excess of either of them. What is identity of metal X? So one thing I kind of just want to comment about this compound, just things I noticed. So X3PO4, you're told X is a metal. Now, PO4, phosphate, has a charge of -3. And if there are 3 of these metals, that means this X has a charge of +1, which means it's either a transition metal, which could have several potential charges, or it's an alkali metal. If you solve for X and guess that it's an alkali earth metal, group 2, you can kind of know from the chemical formula that that's just not possible, right? You can't have this formula with an alkali earth metal. So that's just one little hint that might be able to help you. Okay, so what we're gonna do is solve basically for how many moles of this unknown compound do we have? Because again, we said that they reacted completely. So if we have 11.34 grams of calcium fluoride, we can convert to moles of calcium fluoride using the molar mass. Then 1 mole of calcium fluoride is equal to just 1 mole of calcium. Now the reason I converted to calcium is because I specifically said that calcium and phosphorus, or I'm sorry, not phosphorus, calcium and phosphate reacted to make precipitate, right? A product, which if you look at your solubility table, they actually would be insoluble, okay? And so once we have moles of calcium, we can convert to moles of just phosphate, right? And they were in a 3:2 ratio. And we know that because, oh, sorry, I wrote 2 minus over phosphate. It should be 3 minus, right? Because if you have calcium, phosphate, calcium has a +2 charge, phosphate has a -3 charge. And so for them to be, equal amounts of positive and negative charge, they need to be in a 3:2 ratio like this. Then from moles of phosphate, we can convert to just moles of our unknown compound with our metal, right? And we know that there's 1 mole of phosphate in 1 mole of our unknown compound. Okay, and so if we look at all of our units and cross things out, the number that we get at the end is moles of our unknown X3PO4 compound. Okay. And so from here, we're asked, what's the identity, right? We need to find molar masses. So how can we find the molar mass? Well, the molar mass of this compound is equal to the mass of it divided by the moles of it. Well, we're told at the beginning the mass of it is 20.55 grams. So if we take that and divide it by the moles, 0.0968, that we solved for through the dimensional analysis, we'd find that the molar mass of the entire compound should weigh 212.3 grams per mole. Now, when we're looking at a compound like X3PO4, our overall molar mass would be equal to 3 times the molar mass of metal X plus the molar mass of phosphorus plus 4 times the molar mass of oxygen, right? So oxygen has a molar mass of 16, phosphorus is 30.96, and basically we find that 3 times the molar mass of our metal is equal to 117.33. When we solve for X, we find that the molar mass of X itself is 39.1 grams per mole. When I look in the periodic table, that is equal to potassium, right, K, which makes sense. It's an alkali metal. It typically has a positive 1 charge. So that kind of helps us, I don't know, feel more secure about the math we just completed, okay? Okay, number 4 is a very basic, kind of straightforward combustion problem, okay? And you're asked for the empirical and molecular formula. Okay, and so I'm going to break this up into smaller chunks. And so at first, I'm just going to write my generic formula for combustion reaction, right? My unknown compound reacts with oxygen to make CO2 and water. And I just kind of filled in the amounts that I was given in the problem. Now, at the start of the reaction, all of our carbon and hydrogen are going to be in our unknown compound. But after the reaction occurs, all of our carbon is going to be found as carbon in CO2, and all of our hydrogen is going to be found as in water, right? And so basically, from these masses of CO2 and water, we can find how many grams of carbon and hydrogen came from our original compound, right? So 6.03 grams of CO2, we convert to moles of CO2, and then to moles of just carbon, and use the molar mass of carbon to find how many grams of carbon were in this unknown compound before it reacted and became a part of this CO2, right? So 1.646 grams of carbon would have been found in this original unknown compound. Okay, we do the same thing for hydrogen. So 2.47 grams of water, right? We convert from grams of water to moles of water, and then moles of water to moles of just hydrogen, okay? And then we just simply use the molar mass to convert to grams. And so we find how many grams of hydrogen we had in this original compound, okay? So we know that this original compound weighed 4.837 grams, and we now know how many grams of carbon was in that compound and how many grams of hydrogen. And so the only component that we're missing is oxygen. And so to find the mass of the oxygen, we take the overall mass of our unknown compound and subtract out the mass of carbon and mass of hydrogen that were in that compound that we solved for. And this gives us our mass of oxygen, right? So we have 2.9 grams of oxygen in our compound. Okay, now that we have grams of carbon, grams of hydrogen, and grams of oxygen, we kind of just take our normal empirical formula approach to solve this problem. So we convert from grams of these 3 elements using their molar masses to convert to moles of all 3. Okay, the next step is to divide by the least number of moles. Okay, so the least number of moles is carbon with 0.137. So we're going to divide all these numbers by 0.137, and this will give us a small ratio. Now, sometimes this ratio will be whole numbers. Other times like this, it'll be decimals. Okay, if it's decimals, it should be pretty obvious decimals, like 0.33, 0.5, something like that. Okay, if you ever get these numbers in their decimals, you have to multiply them all by some number to get rid of the decimals, okay? So because it's 1.33, that indicates to me that I need to multiply it by 3 to get rid of my decimals. So I do that, so 1 times 3 is 3, 2 times 3 is 6, and 1.33 times 3 is 4. Okay, and oh, I apologize, I don't have the other picture of this in here. So I'll just talk about it, and yeah, and so that would have been your empirical formula, okay? So your empirical formula would be C3H6O4. Okay, now they told you, let me just go back to the question slide. I again apologize for not having the rest. They tell you that the molar mass of our unknown compound is 424 grams per mole, okay? When we find the molar mass of this empirical formula, C3H6O4, right, the molar mass of that would have been right around 106, okay? And so to get our molecular formula, we would take the molar mass they gave us, which is 424, and you would divide it by the molar mass of our empirical formula, 106, okay? The quotient you get from that would have been 4, okay? To get from the empirical formula to molecular formula, you would just multiply these subscripts by 4. Okay, so your empirical formula is C3H6O4. Your molecular formula should have been C12H24 and O16. Okay, I apologize, and we'll probably make an announcement tomorrow, just kind of stating the answer. I definitely took a picture. I just don't think I realized I didn't have it. I'm sorry about that. So number 5 is how many protons are present in 4.5 grams of water? Okay, so let's just at first look at water, right? So a hydrogen each has 1 proton. Oxygen has 8 protons, right? Those are just those are absolute, right? Oxygen will always have 8 protons, which means H2O has 2 hydrogens and 1 oxygen. We'll have a total of 10 protons per molecule. Okay, so what we do here is we take our 4.5 grams of water, we convert it to moles of water, and we convert moles of water to atoms or molecules, right? Because we're talking about water, right? There's no atom of water, it would be considered a molecule. So in 1 mole of water, we have 6.022 times 10 to the 23rd molecules. And then within one of those atoms dash molecule, right, in this case molecule, we have 10 protons. And so when we do this math out, we would find that in 14.5 grams of water, we would have 4.85 times 10 to the 24th protons. Number 6. Okay, so this one is a precipitation reaction. Again, can pause it now if you want some time to read it. A is classic, net ionic. B, very classic, what's your precipitate? How many grams can you form? C is less common to be asked, but definitely try to understand it, have it in your repertoire of things that you're able to do and understand. But C is asking for molarity of each ion after the reaction is complete. And we're going to really break down this problem. Okay, so at first what I do, right, we have lots of different species with lots of different cations and anions that could potentially form a solid. So I kind of make this list to help me organize it, right? So one of my cations is rubidium, okay? All my potential anions that it could pair up with is chlorine, which it was originally with, phosphate, or sulfate. Okay, and when I check rubidium, if you are unfamiliar with it, it is an alkali metal, just like sodium and potassium. And so when you check your periodic table, you would see that none of these form a precipitate, right? They're all soluble. Okay, one of my other cations is ammonium. And again, ammonium can be paired with phosphate, chlorine, or sulfate. And when I check my solubility table, I see that none of these are insoluble, right? They all dissolve in water and no solid will form. Okay, so lastly, I turn my attention to my third and final cation, calcium. And calcium can be paired with chlorine, sulfate, or phosphate. Okay, when it's paired with chlorine, it would be soluble, right? When it's paired with sulfate, according to our table, it's soluble. But when it's paired with phosphate, we find that it is insoluble. It is a solid, right? It's a gray square, which tells us that calcium phosphate is our precipitate. And remember, when we write a net ionic equation, for a precipitation reaction, we're only on the reactant side going to include the ions that form our solid, right? So calcium 2 plus, and we need 3 of them. Again, they should be in the aqueous state, plus 2 phosphate molecules, each with a -3 charge, again, in the aqueous form. These should go to form calcium, and there should be 3 of them, and phosphate, calcium phosphate, with 3 calciums, 2 phosphates, and they're solid because they form the precipitate. Again, a 3-to-2 ratio of calcium to phosphate, we just know because of their charges, right? Remember, these charges need to cancel. Okay, so again, at the top, we still have that net ionic. That was the answer to part A. But part B asked us, even though we know what our product should be now, is how much can we form? Right, so my top dimensional analysis is solving based on calcium, how much product can we form, right? So calcium came in the form of calcium sulfate in the original problem, and we had 50 milliliters of that. So 50 milliliters of calcium sulfate solution, 1 liter is 1,000 milliliters, and it was a 0.55 molar solution, meaning we have 0.55 moles of calcium sulfate per 1 liter of solution, okay? But look at our net ionic equation. We don't care about calcium sulfate. We only care about calcium. So we're going to convert from moles of calcium sulfate to just moles of calcium. And we know that it takes 3 moles of calcium to make 1 mole of calcium phosphate, our product. Okay? And then to find how many grams of it you could form, you just multiply it by the molar mass, 310 grams per mole. And based on calcium 2 plus ions, we should be able to make 2.84 grams of this solid calcium phosphate. Okay, we're going to do the same exact thing, but with the phosphate. Okay, so phosphate comes in the form of ammonium phosphate, right? There was 75 milliliters of that, so we convert that to liters, so we can use the molarity, right? We get, based on the molarity, there's 0.3 moles of ammonium phosphate in each liter. Okay, and again, look at our net ionic. We don't care about ammonium phosphate. We only care about moles of phosphate. So we're going to convert from moles of ammonium phosphate to phosphate. And then based on our balanced net ionic equation, we know it takes 2 moles of phosphate to make 1 mole of our product calcium phosphate. Again, we multiply it by the molar mass to get it in terms of grams. And we find that based on the phosphate, we could form 3.49 grams of solid. Okay, so how much could you form? Well, you can't make more than 2.84 grams of the product because you would run out of calcium. Okay, so how much can you form? 2.84 grams. Okay, now number 3, it's what is the remaining, what's the molarity at the end of the reaction? So we just kind of found out in the last calculations that calcium is kind of your limiting reagent, really. And so if you're making as much calcium phosphate as possible, calcium, which is limiting, should have 0 molar at the end, right? There shouldn't be any left, okay? And so 0 molar would be your concentration in terms of calcium because it was limiting. Now, the next calculation is for our the molarity of phosphate, which is definitely the hardest one to find it for, because remember, we're going to use some of this phosphate up to make product, okay? And so just like we're solving for excess in a typical limiting reactant problem, right, I'm going to start with how much product I could form based on my limiting reactant, which was calcium. So I could form 2.84 grams of calcium phosphate. I convert this to moles of calcium phosphate, and then I convert to just moles of phosphate, right? In this calculation, which comes out to 0.0183 moles of phosphate, is how much I used, okay? And you might notice that I solved it in terms of moles, because to find molarity, we need it in terms of moles, not grams, okay? And so I find this again calculates how much we use. So we used 0.0183 moles of phosphate, okay? But we never really knew how many moles of phosphate we started with. So that's what this next calculation is. So we had originally started with 75 milliliters of ammonium phosphate, right? I convert this to liters and use my molarity to convert to moles of ammonium phosphate, okay? Now, this conversion tells me that there's 1 mole of phosphate in 1 mole of ammonium phosphate. And so this calculation, this dimensional analysis here, tells me how much or how many moles of phosphate I originally started with. So 0.0225 moles, okay? And so from these numbers, we can find how much excess phosphate we had, right? How much excess or how much remaining phosphate do we have at the end, which was how much we originally had, 0.0225 moles, minus how much we used, 0.0183. And what we find is that we would have 0.0042 moles of excess or remaining phosphate, okay? The last step is they ask you for the molarity, okay? And so the molarity would be equal to the moles of phosphate we have remaining divided by our total volume. Okay, this is really important. Your molarity is your total volume. So it would be your volume of all 3 of those salts together, right? So it was 125 milliliters for one of the salts, 75 for another, 50 milliliters of a third. And so you have to add all of those together. And when you divide the number of moles of phosphate by the total volume, that would give you your molarity remaining at the end, which is 0.0168 molar, okay? Now on this page, I solve, and it kind of says this at the top, this is my calculations for any ions not used in the equation, right? All of these ions were spectator ions, which means the number of moles we had at the beginning should have been how many moles we had at the end. The only thing that changes is the total volume at the end, right? So for example, let's look at rubidium chloride. Rubidium chloride was added as 125 milliliters. Okay, so we convert that to liters, and this solution was 0.25 molar, meaning we had 0.25 moles of rubidium chloride per liter. Okay, now in this dimensional analysis, for example, I'm just solving for rubidium. So 1 mole of rubidium chloride is 1 mole of rubidium. And so at this point, if we were to look at all of our units, we basically solve for how many moles of rubidium we have. So all we want to do is multiply by 1 over the total volume, right? Moles of solute divided by volume, total volume of the solution, and that would give us our molarity at the end for rubidium, okay? We do the same thing for chlorine, right? So again, 125 milliliters of that we started with. There are 0.25 moles of rubidium chloride per 1 liter of solution. 1 mole of rubidium chloride is 1 mole of chlorine. And so at this point, we are at just moles of chlorine. And so we just divide it by the total volume of solution to find our new molarity. Okay, and again, we do the same thing for those other ions. So this third calculation is for ammonium. Okay, so 75 milliliters of ammonium we started with, right? It was a 0.3 molar solution, so 0.3 moles of ammonium phosphate per liter. The important thing about this calculation is that it's 3 moles of ammonium per 1 mole of ammonium phosphate, right? It's not a 1-to-1 ratio, it's a 3-to-1 ratio, okay? But at this point, we have moles of ammonium, and so we just divide by, or really multiply by 1 over the total volume to find that our end concentration of ammonium is 0.27 molar. Okay, lastly, we do the same thing with sulfate. So sulfate was 50 milliliters. It was 0.55 molar, right? So 0.55 moles of calcium sulfate per liter. 1 mole of calcium sulfate has 1 mole of sulfate. Again, multiply by 1 over the total volume to find molarity. Our molarity of sulfate is 0.110 molar. Okay, again, a very classic titration problem. So I'll just let you read this for a second. Okay, and again, feel free to pause at any time to complete these problems before I go over the solutions. Okay, and so one thing I'd notice is that we're given a volume and a molarity of acid. And so that's probably what we're going to start with. And at the end, we're going to be solving for volume of potassium hydroxide, our base. Okay, so again, this is a strong acid, strong base titration, right? Sulfuric acid is a strong acid. Potassium hydroxide is a strong base. Okay, so we start with 175 milliliters of our acid solution, right? We change this to liters, right? 1 liter is 1,000 milliliters, and we use our molarity to convert to moles of sulfuric acid, right? So 0.65 moles per 1 liter. Okay, but again, remember in these problems, we don't care about our total acid. We only care about H plus. And so we're going to convert from 1 mole of sulfuric acid and realize that there are 2 hydrogens in sulfuric acid. So 1 mole of sulfuric acid is 2 moles of H plus. This next conversion should always be in these problems, right? You should always have 1 mole of H plus 1 mole of H plus is equivalent to 1 mole of hydroxide, right? Because this is your net ionic equation for a strong acid, strong base titration. And then there's 1 mole of hydroxide and 1 mole of potassium hydroxide, okay? And then we can convert to the volume of this potassium hydroxide solution by multiplying it by the inverse of its molarity, right? So we put moles on the bottom here, but it was 0.35 molar. So 0.35 moles of potassium hydroxide solution is 1 liter. When you do this dimensional analysis out, it came out to 0.650 liters, or you could have written it as 650 milliliters. You might notice that I wrote it as scientific notation, because if you wrote 650 milliliters, that's technically only 2 significant figures, while this answer should have been 3. But if you got 650 milliliters or 0.650 liters, your math is absolutely correct. An alternative way to do this is use this equation, right, where M is molarity, V is volume, A stands for acid, B for base. I prefer myself to use dimensional analysis, but because I think this equation can be prone to some errors. When you are looking at the molarity of acid or base, for acid, it's molarity of H plus, not just your molarity of the acid itself. It's molarity of H plus. And your molarity of base is your molarity of hydroxide, OH minus, not your overall base. So to solve this one, your molarity of acid, because there's 2 protons in every molecule of sulfuric acid, that means that your molarity in terms of H plus would be 2 times 0.65 molar times the volume of that acid, 175 milliliters, and this would be equal to our molarity of hydroxide, which would be equal to our molarity of potassium hydroxide, times our base that we're solving, our volume of base that we're solving for. And you can see that this method would get you the same exact answer. So whatever you feel more comfortable with works perfectly fine. Okay, so this is a serial dilution question. So the first part is you basically make solution A by dissolving 4.6 grams of sodium carbonate in 25 milliliters of water. After that, you're going to perform 2 dilutions. And I'm basically asking, what is the molarity of your final solution, solution C? Okay, so let's start by finding what's the molarity of that first solution, right? So we had 4.6 grams of sodium carbonate, right? And 1 mole of that weighs 105.99 grams. And so what we find is that there are 0.0434 moles of sodium carbonate. Okay, and so what's the molarity of this solution? Well, the molarity would be equal to moles of that sodium carbonate divided by the volume in terms of liters. And so 25 milliliters is 0.025 liters. And so when you solve for the molarity of solution A, right, your concentration would be 1.736 molar. Okay? Okay, now let's go on to finding information or the molarity for solution B. Right, so to make solution B, they tell you that you take 1 milliliter, right, sorry, let me just go over this equation real quick, right? So this is your classic dilution equation. I'm just writing A's and B's and below B and C to represent what solution I'm talking about. So I'm not talking about acid and base here. I'm talking about molarity of solution A times my volume of solution A is equal to my molarity of solution B times the volume of solution B. Okay, and so we solved that the molarity of solution A is 1.736 molar. Now they told you in the problem that you're going to take 1 milliliter of this, so the volume of that should be 1, and you're going to make it into solution B by adding 1 milliliter of that solution A with 9 milliliters of water, meaning total volume of solution B would be the 9 milliliters of water plus the 1 milliliter from solution A for a total of 10 milliliters. And so when you solve for the molarity of B, it should come out to 0.1736 molar. Okay? And we do the same exact process to find the molarity of solution C, right? So the molarity of solution B times its volume should equal the molarity of C times its volume. Okay, so solution B had a molarity of 0.1736 molar, and they say to in the problem, to make solution C, you use 2 milliliters of that solution. Sorry, my computer is very laggy if you see my mouse going everywhere. Okay, you use 2 milliliters of solution B to make solution C. Okay, and the total volume of solution C you get because you use 2 milliliters from solution B along with 3 milliliters of water. So a total volume of 5 milliliters. Okay, and when you solve for the molarity of C, it would come out to 0.0694 molar. Okay, here's the last one. It is a redox question. Okay, and so what's oxidized? What's the oxidizing agent? How many electrons? And then a bunch of coefficient questions. So questions A and B we can answer pretty early on, and then C through F we'll answer at the end. Okay. So first I'm going to start by assigning my oxidation numbers. Okay, so remember that hydrogen is almost always +1 and oxygen is almost always -2, right? So if silver oxide here, which has, it's a neutral compound, right? Or I guess you could say that it's made of ions. But anyways, oxygen is -2 in oxidation number. And there's 2 silvers that need to kind of cancel out that -2 from oxygen, meaning each one of those silvers needs to have an oxidation number of +1. Okay, CO, carbon monoxide, again, oxygen's -2, therefore carbon needs to be +2 for it to be a neutral compound. Silver solid, that's its naturally occurring state, and so its oxidation number is automatically 0. And then when we look at carbonic acid, right, there's 2 hydrogens, each with an oxidation number of +1. There's 3 oxygens, each with an oxidation number of -2, meaning carbon, for this to be a neutral compound, needs to have an oxidation number of +4. So part A says what's oxidized. Well, we can see pretty clearly that carbon went from an oxidation state of +2 to +4, telling us that's oxidized, right? And we can see from our equation that silver goes from +1 to 0, meaning it's reduced, okay? And so for part B, when they ask what's the oxidizing agent, the oxidizing agent contains the element that's reduced. So we know that silver's reduced. How does that appear on the reactant side? As silver oxide. So that is our oxidizing agent, okay? From here, we're going to balance our half reactions. So we're going to split it up to a half reaction involving carbon and one involving silver. So I'm going to start with my silver one. And so the first thing to do is to balance any non-hydrogen or oxygen atoms. And so we have 2 silvers on our reactant side. And so I'm going to put a 2 in front of my silver on my product side so that those are balanced. Next, I'm going to balance oxygen by adding water. So I have 1 oxygen on my reactant side, 0 on my product side. So I'm going to add a single molecule of water to my product side. Okay. Now I have to balance the hydrogens. So we have 0 hydrogens on our reactant side, but we just added 2 hydrogens in the form of water to our product side. So we have to add 2 molecules of H plus to our reactant side for hydrogen to be balanced. And so now I rewrote my equation now that silver, oxygen, and hydrogen are all balanced. And our last step is just to balance charge. So when we look at our product side, all of these compounds are neutral. So there's 0 charge on the product side. When we look at my reactants, I have 2 protons, each with a +1 charge, and then silver oxide, which is neutral. Therefore, I have a +2 charge on my reactant side. And so I try to make my charges equal by adding electrons, which have negative charge. And so I add 2 electrons to my reactant side to balance the charge. And so right here at the bottom is my balanced half reaction involving silver. All my elements and my charges are completely balanced. Okay, now I turn my attention to the half reaction involving carbon, right? So carbon monoxide goes to carbonic acid. And so first we check, are the carbons balanced? Yes, there's 1 on each side. So let's focus on oxygen. Okay, there's 3 oxygens on the product side, 1 on the reactant side. And so we need to add 2 molecules of water to the reactant side so that we have an equal amount of oxygens on each side. Okay. Now that we've balanced oxygen and carbon, we have to turn our attention to hydrogen. Okay, and so we just added 2 molecules of water, each with 2 hydrogens. So we have 4 hydrogens on the reactant side, and we have 2 hydrogens on the product side, meaning we need to add 2 hydrogens on the product side to have all of our elements be balanced. Okay, and so I just wrote our balanced equation, or mostly balanced, right? All the elements are in balance right here. The last step is just to balance our charge. So our reactant side, all of our compounds are neutral, so 0 charge, which I kind of wrote. And on our product side, we only see charge as H plus, and there's 2 of them. So it has a +2 charge. And so we kind of counteract this or make them equal in terms of charge by adding 2 electrons to the product side. And so right here, I wrote my completely balanced half reaction for carbon, okay? And below it, 2 lines below, this is me just rewriting the balanced half reaction for silver that we made on the previous slide. Okay, one thing we'll notice is we have electrons on opposite sides of the equation. Okay, so we know that we could have maybe made a mistake, but probably not a huge one if electrons are on opposite sides. And what we'll notice is that there's equal amounts of them too. So we actually don't even need to multiply these equations by coefficients because they'll already cancel. And so our step is to add up all of our reactants, right, and write them going to all of our products. We're just combining the half reactions, okay? And once you write them as one big reaction, your next step is to cancel out things seen on both sides. Okay, so there's 2 electrons on both sides, so those completely cancel. On the product side, there's 1 molecule of water. On the reactant side, there's 2. So in the final equation, we should only see a single molecule of water on the reactant side. And this is actually, it's honestly kind of weird. I kind of just happened to make 2 problems in the last week that our hydrogens also cancel out, right? There's 2 hydrogens on either side, meaning those will completely cancel out, and we will see no H plus in our final balanced equation, okay? And I asked you to balance this equation in base, but because we balanced it kind of under acidic conditions and there's no H plus in the balanced equation, this is a balanced redox reaction for acid and basic environments, okay? Again, I did not mean to do that on purpose. It's just how it worked out, okay? And so again, what we balance right here is balance in acid and base. So question C asked how many electrons are transferred. Well, when we had electrons equal on both sides, that's the coefficient they're looking for. So it should have been 2 electrons transferred. Question D either asked for hydroxide or I think it asked for H plus, right? Well, there's no H plus in our final balanced equation. So 0 in what side? Not applicable. right? F, I believe, asks for hydroxide. There's none, so and on neither side, so not applicable. And E was, what's your coefficient of water and what side? Well, it's on the reactant side with a coefficient of 1. So that is the answer. Okay, that is all of me going through these problems. Please let me know if you have any questions, and good luck studying.